First of all, I would like to thank the opportunity to present this topic in this Eurachem workshop. I will briefly describe the aim and the content of the Eurachem draft guide on assessment of qualitative analysis, performance and uncertainty. I will start by discussing how relevant this type of analysis are, the scope of the guide, type of qualitative analysis, how to assess the performance of these methods, how to express the confidence in results, how to report that results, and I will close with some conclusions and recommendations presented in the guide, and I will list the examples from this guide and the working group members. So this analysis or many chemical analyses are extremely relevant because they are used to manage and to protect relevant socioeconomic interests, and many of those involve relevant and challenging qualitative analysis. Some of them are only qualitative, others involve qualitative analysis and afterwards the quantification of the identified analyte. And frequently, or more frequently than we would like, these analyses are not fit for the purpose regarding their reliability. You can assess the fitness of this analysis for the purpose by quantifying the uncertainty from this type of analysis. Although this is not a requirement for the international accreditation nowadays, we can use this way of assessing the performance of this analysis. Accreditation bodies, they request the proof of the fitness of qualitative analysis for the intended use, but they don't ask the quantification of this parameter and even less the reporting of this uncertainty from qualitative analysis. And this uncertainty is rather different from the well-known uncertainty from a measurement. When you have a measurement, you have a confidence interval, and that confidence interval should include the true value of the measurand with a specific confidence level. And in this qualitative analysis, you have not a quantitative parameter, you have a nominal property being reported, present or not present compound, confirmed identity or not confirmed identity of that purified compound. So this binary response or result should be reported with an uncertainty rather different from the measurement uncertainty. Typically, you need to report the probability of that result being correct. The aim of this guide is to assist labs in assessing the performance of these analyses, and if they can, also to evaluate the uncertainty from these chemical analyses. And we have two types of qualitative analysis. We have analysis based on the qualitative criteria, like changing a color, like detection of aliphatic aldehyde in a solution by color change after addition of shift reagent, or any other visual process like identification of human blood type by observation of the agglutination. Sensory analysis are also another example from this type of analysis. But in some cases, you have an instrumental method of analysis supporting your identification, from where you take a quantitative parameter that is typically compared with a threshold, and in that case you have a different way of handling the criteria and handling this type of analysis. Some examples are identification by GCMS or by PCR, where you have that type of analytical instrument. We can even distinguish somehow a third related to the second type of qualitative analysis, that is cases where you have a measurement result, and then you compare it with a maximum or minimum limit, a threshold, and then you report the result as conform or not conform. Somehow you transform a measurement result in a qualitative output, and this type of qualitative analysis is only briefly mentioned in this guide, because you have Eurachem CTAC guide. It was published, the second edition of this guide recently, that discussed that type of analysis in detail. And how can we assess the performance of this analysis? So the easy way is to quantify the rates of true and false results. So first you have to decide what is a positive, what it is defined as a positive and a negative result. Typically a positive result is when you confirm the presence of your analyte. And the negative is when you don't have the evidence of the presence of that analyte. And in that case, to know how good is your method, you have to calculate the true positive rate, that is the probability of a positive case being reported as positive because the result is also positive. In some cases, positive cases give negative results and we have false negatives, and for negative cases you can also calculate the true negatives and the false positive rates. Since true positives and false negatives are complementary, together they sum 100%, we just need one of those. So we just need one of those from the first equation and one of those from the second equation to have a good quantitative parameters of how your analytical method performs in different types of scenarios regarding cases. You can feed these rate calculations by taking a contingency table. So in that case you assess the performance of your analytical method experimentally, and then you organize that information in a contingency table. So for instance, you test 233 cases, positive cases, and 301 negative cases, and you detect how many of these cases are correctly reported as positive or negative, and how many are reported wrongly as negative or positive. For instance, the false positive rate is the ratio of false negative results divided by total number of negative cases. So you have from 301 tested negative cases, you got one false positive, and this is the false positive rates. Typically, the contingency table is built reference to the number of cases. But we must be aware that the contingency table only reports how good is your analytical method, the performance of your analytical method in specific scenarios regarding positive and negative cases. It does not allow you directly to know how good is the result from your unknown sample. If you have an unknown sample and you get a positive result, and if you want to know the probability that that positive result is correct, you need more than just the performance of your analytical method. You need to know something more about the population, the prevalence. You need to know how many cases and negative cases are from the population from where you take the item to be tested. So you must have that prevalence. The prevalence is important, is relevant to close the gap of information that you need to handle to get to that result. For instance, if you have the same COVID test, fast test, being used to assess individuals from different populations, a population where the infection prevalence is very high, and in a case where the population is not very infected, I would say. And if you take individuals from these two populations and you test with this kit and you get a positive result, the positive result is more likely true for the population that has a high prevalence. You can understand better that by using the easy formulas from Bayes' theorem, and you can see that all the conditional probabilities involved require the prevalence to close the gap of information to get that type of output. It is also important to discuss, and it is also discussed in the guide, the challenge that you have to face when you perform this type of analysis and when you assess the performance of this type of analysis. It is particularly difficult to calculate the false positives and the false negative results. In fact, the false positives are even more demanding because typically your analytical methods are very selective, so these false positives can be very low. The first challenge that you have to face is the scope of your analytical method. So you must be aware and know the scope of your analytical methods regarding the property, the metrics, the method, including the identification criteria for the analysis. And after knowing the scope, you have to test the performance of your method for this whole scope. The other thing that you should have in mind is that as you test the performance of this method experimentally, the number of tests will affect how good the performance parameters are. For instance, if you have an analytical method that you test for 50 negative cases and you get only one false positive, so the false positive rate is 2%, you must be aware, and it is discussed in the guide, that this 2% has an uncertainty. In fact, the true value of the false positive rates from testing with 50 negative cases varies between 0.35 and 10%. You must be aware that the true value can be within this interval for 95% confidence level. If you perform 200 analyses, and in this case, if you get 4 false positives, so the same false positive rate, in that case, you can estimate the confidence intervals for the true value of the false positives that will be 0.76 to 4.9. And this is very useful to plan how many tests you need to get reliable false positives or true positive results rates. From this example, you know that if you perform 200 tests, you can prove that false positives will be smaller than 5%. That could be the requirement for your analytical method. So this information is really relevant. But we have a big limitation associated with using this experimental determination of false positive results rates when the false positives is very low. You have a very selective analytical method. A way of handling that could be perform an initial estimate of the false positive result rates, and after that initial assessment, acceptable initial assessment, you start analyzing your unknown samples with extra quality control and confirmation of results. And as you get more information, you will improve your performance estimates, and hopefully you will prove that the method is fit for purpose. An alternative to this strategy applicable to cases where you have instrumental methods of analysis and you have a quantitative criteria for the identification is by developing models of the performance of your instrument, and to simulate what is the chance of an item without the analyte producing by chance a signal above the threshold for the identification. And this is very useful if you have extremely selective identification, just like GCMSMS. How should we express the confidence qualitative analysis results. In somehow, how can we express uncertainty in this case? A convenient way of expressing the performance is by the likelihood ratio, this parameter that derives from the Bayes theorem, is the ratio for some results rates. For positive results, likelihood ratio will be the ratio between true and false positives, and for negative results, likelihood ratio is the ratio between true negatives and false negatives. If you look to these rates, it is really difficult, the interpretation of these rates, because you have two performance parameters that only express the performance of your analytical method. So it is not trivial, the interpretation of these rates. But if you assume that positive results are equally likely than negative results, so positive results is 50% and negative results 50%, so the population is divided in positive and negative results. If you assume that, you can say that for a positive result, a likelihood of 1000 suggests that the positive result is 1000 times more likely true than false. The big advantage of this likelihood ratio is that you can assess the strongness of an evidence. How good is your positive result without the need to assume nothing about the prevalence of results. And this is, for instance, very important to not use prevalence information in forensic analysis, because you don't want to decide about a crime based on previous records of that type of crimes. So they use likelihood ratios for DNA match assessments, and in forensic analysis they suggest that a result, qualitative analysis result, is only binding or associated with very strong evidence if likelihood ratio is above 1 million. This is too strict for some fields like environmental analysis, where typically the likelihood ratio can be much lower. If you identify the polymer type of microplastics, a likelihood ratio above 19 should be okay, because the environmental monitoring of this type of contamination involves the identification of many particles from many samples, so you don't need to be so strict in each identification separately. A nice feature of the likelihood ratio is that if you have two independent tools for your identification, so this means that, for instance, you identify a compound by GCMS and rely on retention times and mass spectrum. If you know the likelihood ratio from identifications based on retention time, and you know likelihood ratio from identification supported on mass spectrum, you just need to multiply both of them to know the likelihood ratio of an identification supported on both retention time and mass spectrum. And if you have additional evidence, you multiply all of them if they are independent. But if you need to know how correct is your positive result, so if likelihood ratio is not okay for you, if you need something more direct to your specific problem, you can calculate the probability of a positive result being correct. But in that case, you must know the prevalence of positive and negative cases. The formula for that, using simplified notation, is this one. So this is the probability of a positive result being correct, and then you have the prevalence of positive and negative results, likelihood ratio of positive results, and as a denominator you have numerator plus 1. If you apply this to a specific case where both positive and negative results are equally likely, and identification is based on a likelihood ratio of 100,000, imagine 100 for retention time plus 1000 for mass spectrum, that gives this 100,000. as a likelihood ratio from both evidences, independent evidences. If you do that calculation, you get the probability of the positive result being correct, that is 99.999%. And you should not do roundings there, because all significant figures here are relevant. You have equivalent formulas for negative cases. Probability of a negative case is being correct. Reporting qualitative analysis information is critical. You must be sure that information is clear, and if you want to report the result with some uncertainty value, you must be sure that parameters are sound and that they will be understood by the someone that will get the report. This guide closes by clarifying that it is crucial to check false positives and false negative results rates. You can report performance through a likelihood ratio. This is a very convenient way, but probably most importantly, your analysis must be based on adequate references, adequate identification criteria, and you should be careful when you decide to report the results with uncertainty, that to avoid any misinterpretation. The guide has 6 examples from chemical and clinical analysis where all these concepts are applied and discussed. All difficulties, so how to use a database for edification, uncertainty evaluation, and but most importantly, I would like to list the current working group members. I would like to thank all of them for their contributions that were very useful to the preparation of this guide. Some people were involved in the initial part of the working group, are not listed here, but they were also very important for this work. The guide was distributed for voting, so if you are involved in the voting process, please send your vote, send your comments by July 5th. Thank you very much for all your attention.